webinar. So the title of this talk, the title of the talk is IC inspection and failure analysis using single photon detection. We started with this topic as part of a research project on this, in which several universities, research institutes, and manufacturer of security ICs work together. And maybe in this case, when I talk about security ICs, I mean integrated circuits that are used in ID cards, passports, or smart cards, for instance. And the aim of this project was to evaluate the robustness of security ICs against physical side channel attacks, especially against optical side channel attacks. And here in this field is whether an IC is at risk from a side channel attack essentially depends on the effort required for the attack. So that means the relevance of such a particular side channel attack increases with the simplicity of the hardware. Therefore, our goal in this project was to create a laboratory setup that is as simple and inexpensive as possible, as well as modular, highly flexible, so that we can easily adapt to new analysis methods and different integrated circuits. So, and in the following or next 30 minutes, I will introduce this IC inspector, as we call it, and will show you some of our results we gained with it. So first, of course, I will introduce the IC inspector. And before I can talk about what we can do with this, I have to show you also what we have to do with the ICs. Because what you want to do at the signal propagation, you want to track the signal in the IC by an optical method. So that means somehow we have to prepare an IC to be able to look at it during the operation. Then I will show you briefly 4 of our 5 methods that we can use: classical near microscopy, Obik, and then I will focus a little bit more on the 5th, the photon emission analysis, because this is the technique where we use single photon detection. And I will show you what you can do with, what is possible there. Okay, with this, let's start with our device. As I said, the topic was to implement as many techniques as possible for analyzing the operation of an IC and make it as inexpensive as possible. So what you can see here is the schematic drawing of the setup. It consists of 2 parts. The main part is a near-infrared microscope. You can see here. It is equipped with 2 detectors, a silicon-based CCD. It's a near-enhanced one. That means the quantum efficiency at 1000 nanometer is still 30%. And and this is used for integrated images. And for temporary solutions, if you're interested to look at this signal propagation to an IC, we use an INGAS spot. It means a single photon avalanche detector optimized for the near-infrared range. And the second part is a laser scanning module consisting of 2 independent lasers. These lasers, each laser has its own scanning module. That means the lasers are focused onto our device under test. That means our ICs. And within the field of view, we can position each laser at different positions at the same time. Also, we can we can trigger a laser pulse at the same time or different times of each laser. And this is the setup. And as you can see, we have 4 different ports. We can connect to these ports also different other detectors. Let's say we can also add here a different laser for TLS, for instance. This is in general. I will explain later why we have here different optical paths for different wavelengths. This is related to the device under test, which is a silicon-based integrated circuit. So that means silicon is not transparent for visible light. And also it's related to the spectral range of the photon emission. I will explain it later in detail. So to sum up what we can do with our setup or what it offers, as you can see on the right in the picture, this is our setup in the lab. It's quite compact. The dimensions are, in these dimensions, we have here a length of around 100 centimeter. The depth is around 50 centimeters and the height is around 40 centimeters. We put it in a near opaque enclosure because we want to detect single photons in the near infrared region. So that means we have to block every light from the ambient light from the room. Our system is quite compact. This is highly modular, so we can adapt easily to new analysis methods and also different ICs. This is the main feature of our system. What you can see here, this is the area where we put the device under test. This here region is the near-infrared microscope. This spot you can't see is connected via a fiber here. And in this region here, we have our laser scanning modules. The laser scanning modules allow us to do to do some of our analysis really fast. We are usually not limited by our system, but by the detection of the signals or of the data. And what we can, the positioning, if you move the laser within the field of view of an objective, we have a precision of the positioning of less than 100 nanometer. And as I will show you later, for optical measurements, it's possible to have a timing precision better than 10 picosecond. The way we designed our setup and realized it allows us that we do not need a clean room environment, we do not need sophisticated vibration isolation, and no liquid nitrogen cooling is required for the CCD. Yeah, as I said, this is our setup. The DAT will be placed here, the device under test. And the question is now, how does the IC is prepared for our measurements? I think many of you know how IC is built up. You have a substrate. On top of the substrate, you have your transistor level. And above the transistor level, you have the metal interconnect layers. And if you have a very dense IC, what is usually the case, that means you have also very dense layers of metal interconnectors. So that means from the front side, it's almost impossible to do optical analysis. Of course, you can remove and rebound everything, but that's too complicated and takes a lot of effort. So we thought about why not going through the back side. Here, what you can see are 3 steps of opening a package and thinning the substrate in the end. So we have here, this is an FPGA. We open it from the back side. We thinned it down to the frame, lead frame. So what you can see here is already the substrate. That's the die on which the transistor level is placed. Then we remove the father. This lead frame is quite special here. And in the last step, we thin the substrate down to usually a remaining thickness of 10 micrometer. Substrate usually, or the thickness of a substrate a substrate has a thickness usually of several hundred micrometers up to a millimeter. We have to thin it down. And at the end, the last step is to polish the surface. This polishing is required if you want to have the highest spatial resolution you can achieve with your setup. It's required in our case because, as you can see here, silicon is not transparent for visible light. So we eliminate this in photo taken with visible light, and you can't see through the silicon substrate. And this also explains why we have to use wavelengths for lasers and others in the near infrared region. Yeah, okay, but this is what we have to do. And when we have this, we can start. And we have, as I mentioned, 5 different modes of operations or techniques we can use for analyzing IC. The first one, when we start with a new IC, is of course classical microscopy with near-infrared light. So in our case, we have a dark field reflected light microscope, and we use as illumination LED with at a wavelength of 900 nanometer. 900 nanometer is still absorbed, but most of the energy nevertheless can pass the substrate twice. And what you can see here is an overview image taken from 50 microscope images. But what you can see here is the reflected light of our illumination at the metal layers. In a near-infrared image, you always see the metal layers, not a transistor level. This cannot be seen here. So that means if we change the focus a little bit, you will see a little bit different image as you look at a different metal layer in the depth. But nevertheless, near microscopy helps you to see, the internal structure. It identifies the places where you want to do the analysis later, but it's limited. More precise is if you use a method called Obik. Obik means optical beam induced current. It's a standard for failure analysis, but you can also use it to orientate yourself on an IC. Obik is done by using a laser, scanning with the laser over your IC. And the wavelength or the energy of the laser is above the semiconductor bandgap energy. That means with the laser, we can produce free charges. So that means what happens when we scan over the IC, we generate a photocurrent everywhere. And what you have to do, you have to measure it somewhere. And in this example, we measure the photocurrent between the power supply and the grounding pin of an IC. And the question is now, what is it what you see? So let's start with an example. Here's an example of such a measurement. And what you see here, if you look here or if you zoom in, you see the the electronic structure of this IC or defects. Defect would be, if you have a defect, that means we will have a black area somewhere. But what you see here are PN junctions of transistors or diodes that somehow are connected to the pins where we measure the photocurrent. Light is absorbed everywhere, also on the substrate, but only by the intrinsic field of the PN junction. These free charges are separated and generating a photocurrent, and only the photocurrent or the PN junctions, and therefore the photocurrent that is created there, that is connected to the pins we are using, is what we can measure. So that means if we use different pins, it might be that we see only here bright areas and everything else is dark. It depends on where we measure. So this is Obik. This is a really good feature or a tool to do failure analysis and also to orientate on an IC. Because here we are on the transistor level, no longer on the metal layer plane. Similar to Obik is a method we use for side channel attacks, for analyzing the robustness of these security features of these security ICs. And this is called laser fault injection analysis. Here we again generate free charges, but want to altering the logical state of the transistor or logical element. So it's done similar, but in this case here, the IC is running. So it means we are connected to the power supply voltage, and the laser again is scanning over an IC. And now we're creating many free charges, and we hope that this is sufficient enough that the current that is caused by that can alter the state of a transistor or logical group. So that means after scanning with the laser, or while we're scanning the laser, we have also to check what has been changed during the illumination with the laser. Simple example that shows what's possible is the manipulation of the state of an SRAM cell. If you look at the circuitry here of an SRAM cell, this is the standard SRAM cell you find in each controller and on each integrated circuit. That means this is 1 bit. It consists of 6 transistors. And I will not explain in detail, but as here is highlight, there are 6 sensitive areas where you can set or reset. That means you can change the red ones, the state of this SRAM cell from 0 to 1. And in the blue regions, you can set it from 1 to 0. So, and here's a result of such a scan. We scanned a memory block. It's a bigger one. We scanned with the laser over it, and we varied the laser intensity. We started quite low, and as it seems here you can see the laser power we used. We start obviously the threshold for altering the state of an SRAM starts at 50 milliwatts in this case here, and then we increase the power slightly, as you can see, and then all the others 4 remaining sensitive areas appeared. And what you can see here is that each of these 6 transistors, or these p-n junctions, are clearly visible in our scan. So that means we were able to trigger all these 6 sensitive areas to change the state of this SRAM cell. And this state is stable. So that means if you trigger here a short current, you alter the state of it, and after altering, it's stable. It stays there until you change it again. So that shows that you can use lasers to somehow change the operation in integrated circuit. So as a last example for a laser method is thermal laser stimulation. This is mainly used for side channel analysis, but can also be used for failure analysis. Here, the principle is similar. We are going with a laser over the IC, but this time the photon energy is less the bandgap energy. That means we are not able to generate free charges. But what we can do is we can heat up, let's say, the metal contact between the gate and the metal interconnection layer. And if we heat it up, we can generate by the Seebeck effect a small voltage. And what happens if the transistor is usually switched off and we introduce to it a small voltage, we also induce a small leakage current. So that means with TLS, we have a technique to detect the state of a transistor. A switched off the transistor, in such a transistor, we can induce a leakage current, and a switched on, we can't. So that's what we have, what we see then if we do such a scan. The challenge here is measuring a leakage current while an IC is running. This is really hard. It's not easy, and in some cases it's not working. So, but what can you do with it? In side channel analysis, it was used for reading out memory, the memory of an IC, because we know the state. You have seen in the previous slide that an SRAM cell has 6 transistors, and the information is stored by 4 transistors, and always 2 transistors are switched on and 2 switched off. So that means depending on which of these transistors is switched on or off, you get the information what is stored in this single cell. And that's what we did here. We used as an example the memory block in our microcontroller. We programmed it that way that when we scanned this memory block with TLS, it reveals our DLR logo. You can see here our DLR logo, and you find it again in this TLS scan of this memory block. So, and as we can here also not only scan memory cells, we see the state of a transistor. This tool can be used for failure analysis too, because here we use a wavelength that is not absorbed by the substrate. So that means you do not have to thin the substrate for this kind of measurement or analysis. So this is a great tool. So these was the last of the laser techniques. Now I come to the main part of my talk, the photon emission analysis. It's used for failure localization, but also for side channel analysis. So what is photon emission, where it comes from? Photon emission occurs when a transistor operates in saturation mode. This is true for all integrated circuits, as long as it's true, and when a current flows. So that means if we have, you know, that in integrated circuits we have PMOS and NMOS, from which all the loggages are made of. So that means if they are switched off, there is no photon emission. If a transistor is switched on, as shown here, there is a current that flows from the source to the drain due to the voltage, supply voltage attached to the device. So, and by the transition, the electrons gain energy. And close to the drain, they gain that much energy that they can emit a photon by direct or indirect transitions. So from that, it's also clear that the properties of this photon emission depends on the voltage level. So that means lower voltage will cause a different spectral response or spectral photon emission. And also, when we talk about how many photons can be generated by electrons, of course, it shouldn't be one, because if we have 1 photon per electron, we could call this device LED. So it's obvious that the number is quite slim. So the spectral range starts, depending on the applied voltage, in the visible range towards the infrared range. The maximum of the photon emission is usually in the near infrared and shifts for lower voltages toward the infrared region. Coming back to the probability of the emission of a photon, the probability is around 10⁻⁴ to 10⁻⁶ photons per electrons that go through the conductive channel. That means to emit, in the worst case, that one photon is emitted, 1 million electrons have to travel through this conductive band. And that shows you why we need single photon detection to do photon emission analysis. So let's come back to the setup. I explained or mentioned that we have different wavelengths here. As I mentioned, part of the photon emission, or there's a tail of the photon emission in the visible range, and we are detecting this part with the silicon CCD. We are using this to get an overview image, to get an integrated image over the photon emission, as an example is shown here. You see here a simple microcontroller, and each bright dot is a transistor that emits photons. And from these pictures, for instance, if you now change, let's say you switch on off some functionalities or so, you can learn what is the function of certain areas. For instance, we found out that this area, here we zoomed in, is part of the memory controller. So when you access the memory, the address will be set here, and also the content of the memory go through these transistors. So that means if you look at these transistors, you can gain some information what is stored in the memory. And for this measurement, we use a temporal analysis. And for this, we use this single photon avalanche diode detector. And what you get then is you see a temporal signal. And in this case, this is not in security IC, so no protection. So it was quite easy here to determine from this temporal signal the key of the AES encryption. But it shows what is possible. The question is now, what are the limits of this method? The spatial resolution, as I mentioned, depends on on the wavelength. That means for the lasers, when we use the lasers, or of the photon emission, and also the purge of our microscope. But what is the time limit? How far can we go down? So this, for this, I want to show you or explain how picosecond imaging is done. This is a really nice technique. And what you want to do here is you are not interested only in the information when a transistor emits a photon, but also how this time event changes. Is there a delay when we change something, let's say in the logic before? Let's say another transistor is involved, and so we have an additional delay in a propagation. So the question is, what is the limit for resolving such a difference in the signal propagation? For picosecond imaging, we start in the same way. We start with a near microscope image. This is the gray picture you can see here. Then we take a photon emission image with the CCD. And what you see there is here, the red dots. These are the transistors that emit photons during the operation we are looking at. So it seems that all these transistors somehow are related to our operation. So that means for the next step, we do not have to go over all the area. We have only to go to these transistors with the, we have to position it, the device on a target in that way that we can analyze the temporal behavior with the spot. So, and how is this done? This is shown here. We have our device. It's powered up and running. We need some input. It can be a clock. It can be anything. And we use also this signal as a reference for the time tagging, because we have somehow to correlate the photons to our process. With the INGA spot, this is an ID 220. We are using in a multi-mode fiber configuration. Each photon that is detected releases a signal, and the signal is triggered or is time tagged in reference to to the input signal. Depending on the process, how long the cycle is you're looking at, you can do the correlation in the TDC, or this is what we had to do for this kind of measurement. We stream the time tags of the reference and the received photon signal to the PC and do the correlation later. As you can see here is the TDC. We use the ID800. This one is no longer available, but the ID900 works in the same way. And it's maybe a little bit better, especially when we talk about time resolution. So the question is now, or let's explain. Yeah, we have here a transistor. And as I said, we're interested to see what happens if we change something. Or let's say we look at this one and to get by this measurement, something like this. You see a time signal with 2 periods. And let's say the next one, we will do a measurement here. We expect a similar temporal image, but shifted. And the question is, how close can these two events happen? So if you look at the TDC, the time base is 81 picosecond. The jitter of the ID220 is around 180 picosecond. So you would say that's not much temporal resolution or precision. But we can assume, as the time base of the TDC is 81 picosecond, that the internal more precise. So we think that should be possible. But first, the question is, what is the overall jitter of our system? We measured it for a single photon. This is the overall jitter of the TDC, of the spot detector, and of our device under test. And the advantage we have here in a photon emission, the probability to detect 2 photon events at the same time, this is really unlikely. So that means each photon we detect is independent from the other detected photon. So that means if you repeat a measurement 1,000, 100,000, million, billion times, what you will see is not a jitter alone. You will get a statistical response from the system, from your measurement, and you get Gaussian distribution for this single event. So that means we look at one transistor in a certain configuration, let's say, and we want to measure the time of this event when it emits a photon. We repeat it quite often. So, and then let's say we change something. We made sure that maybe another transistor is involved in the propagation chain of the signal. And so we expect, if we do the measurement again in the second configuration, that there is a slight change in time. And we repeat the measurement again 1 billion times. And what you get then is something like you can see here. You get 2 Gaussian distributions for these 2 different events. And if you compare the center of these Gaussian distributions and measure the difference, you will see that you can achieve a precision that's less than the binwidth of the TDC. And in our case, we achieved a precision of 6 picosecond. To show that this really is possible and what you can do with this, we created a video of an inverter chain. I hope the frame rate is for you okay. You see here in CPLD, we programmed there an inverter chain of 10 elements, as you can see on the top here. This is the single logical element where the logic happens. And what you can see is the photon emission that happens during the operation. And you can see that the signal travels from the left to the right. And if you look here, we here rounded the precision to 10 picosecond, but it's sufficient. So here on the top, we have the inputs, and at the bottom are the outputs of such a logical element. And what you can see here, we have now the big one emitting. So here's the small one. These are the output transistors. It's a PMOS and the NMOS. You can see, and they have to change. For one logical element, it has a big. For the next, it has to be the small one, because the logical state is changing. And the reason, or what is also quite interesting here, what you have seen, a different size of the PMOS and the NMOS. The big areas, the big transistors are the PMOS, and the small ones are the NMOS transistors. This is because the mobility of the electrons is in an NMOS higher, 3 times higher than of holes for a PMOS. And to compensate for this difference in the mobility, the PMOS are usually bigger in size. Yeah, this shows you what you can do with picosecond imaging analysis, and it shows you also that we are able to track the signal within through an IC by an optical method. So with this, I come to the end of my talk. I showed you our setup, and the latest result, well, the last slide, I showed you that we are able to track the signal in IC by an optical measurement in a fully operating on a gate and transistor level. By using this kind of temporal super resolution, we achieved timing precision for this optical measurements of less than 10 picosecond. And yeah, this is quite nice. And what distinguishes our setup from other setups like the Hamamatsu FEMO system, or from SemiCap or TLS systems from Alphanov, is that we can use in our setup 5 different methods without having to make additional modifications or adjustment to the systems. We can use them not at the same time, but we can use them without any changes to the setup. And this is really nice. And also our modular design allows us to adapt easily to new ICs or also to new analyzing methods. I showed you only the analyzing methods available, but for doing a side channel, you have to combine these different methods, and this is quite tricky, but our modular designs allows us to switch easily to different configurations and perform excellent. Yeah, with this, thank you very much for listening. And in case I'm not able to answer today all questions, or you want to have some more information or want to see our system, please feel free to contact me. Thanks.
Thank you, Sven. Thank you very much for this very interesting presentation. And now we're going to take questions. So if you have questions, you can type in your questions in the dialog box that you have in your interface. And before we're going to take questions from the audience, I know Felix, you had a question.
Yes, I do have a question. So thank you very much, Sven. It was very interesting. I wanted to ask about the wavelength range that you know, of this photo emission. You have been doing measurements with the ID220, so 1310, 1550 in that region. Is there, does it extend? Does this photo emission extends below that range and also possibly above? And what would make it extend, for instance, in the longer wavelength region?
Well, first is it depends also on the kind of semiconductor. If you have gallium nitride, for instance, for power electronics or whatever, the emission is shifted more, or it happens, the maximum of the photo emission is in the visible range around 700 nanometers. But here in the silicon-based ones, it's always the maximum is in a near infrared towards the infrared. But so far, the problem is if it shifts more to the infrared, it's really getting difficult to measure it. You have to start, yeah, it's not only that or in the case when it happens to shift, it also means that the voltage of an integrated circuit was reduced further. And that means also that the number of electrons flowing through such a transistor is reduced. So that means you shift the wavelength to the infrared and you reduce the intensity. So there's a point where you can't measure it anymore. So this is more some critical point. So this is the limit of photon emission that will become. So so far we compared different feature sizes. We did the smallest one was 60 nanometers, and so far it worked with in the near infrared very well with the ID220. But for the silicon-based CCD, this is a critical issue. That means if you're interested in CC or camera image, then you have to switch to an in-gas camera. But this camera has to be cooled by liquid nitrogen because usually these detectors have a really high dark count range.
Is it maybe you said that and I missed it, but is it related to the power? You know, when you move to ICs with smaller feature sizes and then lower power consumption, do you also, in a way, does it mean that you're going to have longer wavelength emission photons, or not at all? Let's say for the same material, or maybe other materials give you that. And I know it's a complicated question. Maybe
it means for lower voltage, it means the energy distribution that is of the electron is reduced because the maximum energy the electron can gain is this voltage. So let's say you have a volt, it means the energy, kinetic energy is 1 volt, and that limits your wavelengths, your shortest wavelength. So that means for shorter voltages, the photon emissions is completely shifted towards the near infrared, the infrared region. Okay. So that means there is at some point no photon emission in the visible range.
Has anyone, do you know if anyone did IC inspection with a detector that was working beyond 1550?
No.
No, okay.
So far, the problem is, as I said, there are two things. First is the wavelengths, of course, and the intensity. So that means if you go to the infrared, so usually noise is the critical point here is the dark count rate. And this is always for in-gas systems difficult issue, and for infrared detectors it's a little bit more. So that makes it so difficult. And right now, in-gas technology is, I think, the best technology available for this kind of analysis.
Okay, thank you. We have a couple of questions. The first question is about the troubleshooting capability of your IC inspector, and to check the operation of ICs at different temperatures by varying, I guess, the temperature of the chip. Is it something that you've done, or is it something that is possible?
This can be done. It has been done. The results are not so. Yeah, some showed that there can be the photon emission can benefit. Also, our laser photon injection can benefit from heating it up or cooling it down. More from heating it up. We don't have done it.
Okay.
But it has been done before. But the benefit wasn't that huge, so we decided to skip this part.
Right. Okay. Excellent. The other question is, what are the limitation in terms? I guess the overall beam is diffraction limited, right? So in terms of IC inspection, what limits does it set?
Yes, as I said, our system is diffraction limited, so that means the spot size of the laser, or if you talk about the spatial resolution of the photon emission, is defined by the wavelengths and the numerical aperture of the microscope objective we are using. So right now it's for photon emission and near-infrared microscopy is around 1 micrometer right now in the current configuration we're using. And the laser spot has a smallest diameter is around 600, 700 nanometers right now. We're using an objective with a numerical aperture of 0.85. But if you want to reduce these numbers, then you have to use different objectives. Let's say you go to all immersion lenses, then you can achieve a numerical aperture, I would say up to 1.5. So then you can gain. If you go to solid immersion lenses, there you can achieve a numerical aperture up to 4. And that means then you can go down to a spot size of, I would say, 200 nanometers, something around that.
Okay, so I guess that answers the question. There's another question on certification of ICs. What is the current situation? Is there a chance that this becomes some sort of required or mandatory testing for security chips?
It's already required. So that means if a company sells such devices like security ICs, they have to show that they are robust against well-known side channel attacks. So they have also to prove that they are. The thing is, when we can alter an operation or a transistor by light, it means in general these integrated circuits are sensitive to light. So that means in general you have to also make sure that not when someone is using a flashlight, he can alter somehow the logic or the operation. So that means these ICs have to be tested, and they have to show that they are robust against certain attacks, well-known attacks. And as I mentioned, of course, not every attack is yeah, well, if you see that you are vulnerable at one point, then you have to think about countermeasures in place. And of course, if you find out that the effort, or let's say the system you need for doing this, is so expensive and it takes that amount of time that it's unrealistic that a simple hacker or even well-trained hacker will do this, then of course you can ignore this kind of side channel attacks. So that means it's quite important that the system is. That's what we did. It must be highly reliable, and so if you repeat measurements, it should be always the same outcome, but it shouldn't be that expensive. So that means we have to compromise somehow. So this was, for instance, one of the limitations for us. But in general, yes, to answer this, these ICs have to be certified.
Okay, thank you for the clarification. Felix, any?
No, I'm okay.
Any other question? No. I don't see any further questions. So I think this will end this webinar. And I'd like to thank one more time. I'd like to thank you, Sven, for taking the time to present your activities and introduce us to this new technique, which is quite fascinating, I have to say, and promising. So thank you again. And I wish everyone a nice day, a good evening. Before you go, I'm going to just pull up a poll. So if you can take the time to answer the question that's going to come up, that would be quite appreciated. And I'd like to also inform you that there's going to be a next webinar in September. Check our website for the date of the coming webinar. And at the same time, I also would like to remind you that all are available for replay on our website. So don't hesitate to look at the previous webinars if you haven't had a chance to attend these previous webinars. So thank you very much again, and I hope to see you soon.
Bye.